And there's been some up-to-date information that we didn't have before that I'm going to share with you towards the end of this. Asteroids sort of are what we think of as a fossil of the solar system. And the main reason we think of that as perhaps a fossil is, if you look at the definition of a fossil, it's a remnant, impression, or trace of an organism. Obviously, we're not talking about organism here, of a past geologic age that has been preserved in the Earth's crust. Well, preserved in the solar system instead. And so it's very similar to what fossils are on Earth. And these are some of the fossils on Earth. Oops. And these are some of the fossils that we're going to be talking about in the solar system. Very similar in a lot of different ways. And so I'm going to try and answer three questions. One is, and these are in pretty much almost everybody's minds when you think about asteroids. One, is it a danger? Okay, that's the first one. That's on everybody's mind. Two, can they be used in some way? And if you're a sci-fi fan, you see videos or images or movies about, a group of people going and like tugging a asteroid into Earth orbit and using it. And that's sci-fi at this point anyway. And then the third thing is, and this is the thing that's near and dear to my own heart most, is what can they tell us? And I'm going to share some information about that. So, are there danger and is there a defense? Well, if you look at this image, this is the sun, so Mercury, Venus, Earth. These are asteroids. Okay? Don't get scared. Okay? It looks like we are amidst a swarm of asteroids, and one's going to hit us any day now. That's not exactly the case. If you look at big ones that happen, the 5 to 10 kilometer range, which is sort of a near or is a near extinction event, happen roughly about every 100 million years. So none's expected anytime soon. 1 kilometer range, about every 500,000 years. 300 meters, maybe a few, every few thousand years. And then a 20 meter one, like Tunguska, is about every 100 years. So we're due for a 20 meter one, but not necessarily. These are just approximates and sort of chance events. In terms of how many asteroids are around, we think that within 100 million miles of Earth, there's maybe 30,000 asteroids. Okay? We characterize the ones that are dangerous as potentially hazardous objects, PHOs. And then, so within 4.5 million miles of Earth and greater than 140 meters, and these would be the ones that could hurt us. Talking about maybe about 2,000 asteroids. Most of these won't be anywhere near us within the next 1,000 years. The only ones in the next 100 years that'll be near Earth are about 17. And near Earth means within, let's say, a few 100,000 miles or more.
Who's doing that, Neal? Who's?
These are approximations, and I'll get to how we're trying to figure that out.
Okay.
If you look at the size of asteroids, this is a 1.4 kilometer asteroid. You see how big that is? The problem with an asteroid is you think of it as dropping and just wiping out part of the city. if this thing hit, it would hit with enough force to eliminate probably half the United States. Because of the kinetic energy.
What would be the velocity?
The velocity would be at least 25,000 miles per hour, probably a lot more than that. Probably in the range of 40,000, something like that. 1.1 kilometer would be this. The smallest one, Apophis, which is one that was being predicted as hitting us in 2029. We now know it's probably not going to come that close to us. But that's about how big it would be, about 370 meters.
Was that about the size of the one that the meteor crater up in Arizona?
No, it was smaller.
It was smaller than that.
Yeah,
It was about a 50 meter asteroid.
Do these things burn up at all coming through the atmosphere?
It depends on the type of atmosphere. Asteroid, I'll get to that in a minute. So basically, with near-Earth asteroids, we need to know when the impacts could occur on human timescales and how bad they would be. When comes from finding the objects and determining good orbits for them. If you know an orbit, you know basically how close they're going to go. And that's why we're able to figure out that Apophis, for example, is not likely to hit us. How bad it's going to be if it does hit us comes from measuring the impact energy. And the impact energy is very simple as mass times velocity squared. So, excuse me a minute. The velocity comes from its orbit. You can figure out how much it's going to hit you by its velocity. Usually in a range, escape velocity from Earth is 25,000 miles per hour, give or take. They can go up to 50,000, 100,000 miles an hour, but not more than that usually. And the mass is density times volume. So basically, the impact energy depends strongly on the size of the object. So what should we do about this? Well, Congress passed the George E. Brown Survey Act, which said NASA should discover 90% of NEOs, near-Earth orbits, objects, larger than 140 meters by 2020. That has come and passed. So far, only about a third have been found to date. The rest are undiscovered. So basically, we don't know the majority of the ones that are out there. NASA is planning on a satellite that will detect it. And that's called the NEO Surveyor, which is a planetary defense mechanism designed to detect, track, characterize the small bodies, and then figure out what to do if one's going to be coming close. NEO Surveyor provides information to anybody who needs to know what to do in terms of mitigation. What do we mean by mitigation? I'll get to that in a minute. So the Near-Earth Orbit Surveyor is going to be able to discover probably about 300,000 new near-Earth objects. And probably millions of the main belt asteroids. Those are the ones that are between Mars and Jupiter. So it's a significant improvement on the number of asteroids that are known today. The way it's going to do this is by not using visualization of asteroids, but rather infrared determination of asteroids. The reason for that is about a quarter to a third of near-Earth objects are very dark, and you can't see them, even with a telescope. But they are very bright in thermal infrared wavelengths because traveling through the solar system, especially when they get close to Earth, they warm up a lot. Okay, not even touching Earth's atmosphere. Just being near the sun, they warm up and give off
Oh, wow.
heat. So basically, that'll allow us to detect these asteroids even if we can't see them. We can detect them in infrared measurements. The NEO surveyor will be at one of the Lagrange points because that's the best place of using IR. One of the Lagrange points, L2, is where the James Webb Space Telescope is located. Because you can put a shade up and you face deep space, and so you can, with a tank of liquid helium, you could get down to about 7 Kelvin, meaning 7 degrees above absolute zero. And that allows you to see anything that's warmer than that.
Explain Lagrange points.
So the Lagrange points are places where the gravity of Earth and the gravity of the sun sort of balance each other. So that basically if you have something that orbits the Lagrange point, it doesn't do it absolutely, but you have to use very little fuel to nudge it once in a while to keep that orbit, rather than an orbit around Earth or an orbit around the sun where you're losing time because of the fact that oftentimes the sun will come between you, etc. Here, all you get is dark sky constantly, and you can basically stay in that area.
Someday I'll ask you, not now, why L2 and L3 are Lagrange points, which I didn't understand, but not now. Keep going.
Okay. I'll talk to you about it offline. Okay. All right. So, what can you do? Mitigation strategies. What can you do? Well, basically, this is a map, and I'll show you what the timeline actually is. But you'll notice that basically, the bigger it is, the more time you need. Okay? If you want to try and deflect one, nudge it with an impactor, you need 20 years lead time. Okay? If you want to really do anything. 7 years out with an impactor is problematic. The reason being, they did computer simulations, and they found that multiple of the missions that were done, some of them failed. For example, the asteroid was deflected. Denver was saved. It was headed for Denver. Denver was saved. But a big fragment hit New York City with a 10 megaton blast. Oops, sorry. It's one of those kinds of things. So 7 years, even 7 years is problematic. 6 months out, the only thing you can do is evacuation of the damaged zone. If it's big enough that you're having an extinction level event, there is nothing you can do. And that's it for the human race. Now the good thing is we don't have any evidence of any kind of near-Earth object that's big anywhere near us within the next 1,000 years.
So your third line says can use a 1-ton kinetic impactor.
Right.
1 ton meaning just something that heavy?
Yes.
Okay, not blow it up, turn into a shotgun shell.
No. Just a pure impactor, like the DART mission that did that with, I forget the asteroid, but they sent up just as a demonstrator, and they were able to move it off its orbit.
It moved off its orbit by changing the velocity to feet per second or whatever, and not even very much, as I recall.
Correct. But if it's big enough, you need enough impact and enough lead time to be able to get it so it's not going to be anywhere near Earth.
So, Neal,
Yeah.
when you say you need 20 years, what are we gonna be doing in those 20 years?
First of all, like I said, developed a near-Earth object satellite that will be able to detect them, so we know where they are. And then, once we know where they are, we'll know their orbit. And if any of them look like they're going to be coming close to Earth, we can develop strategies as to what to do.
Like build a rocket and,
We already have the rockets. The question is, how do you arrange it so that it hits it the right way, so that that's not going to come near Earth?
and that math takes 20 years? Or 10 years or something?
About that.
So, actually,
Yeah.
like bombing it or something is not a
That's not an option.
option.
What happens is if you send up nuclear weapons, you're breaking pieces off, but those pieces are headed for Earth anyway. And so what you've done is taken one chunk, now making it in multiple chunks. So instead of just New York getting hit, now it's New York, Washington, Philadelphia, Denver, San Diego.
How about Russia? Anywhere in Russia?
Depends on where it's headed. So let's talk about, can they be used? If you're thinking of mining asteroids for minerals, it's very complex and very expensive and very much beyond our technology today. Okay? So that is possible, but way in the future. We're not thinking about that now. The thing that we can mine it for is water, because there's oftentimes water trapped in these asteroids. You'll see that in a minute when I talk about it. Okay? Water can be used for rocket fuel. So if you wanted to explore space, bringing everything you need from Earth is absolutely ludicrous. Think about the Lewis and Clark expedition. Okay. It lasted 863 days. That's about right for an expedition to an asteroid, let's say, right? Crew of 45 people, maybe not that many, but you've got to have a fair number of people. And they travel 8,000 miles as opposed to the millions of miles we would be traveling, or hundreds of millions of miles.
They were walking, by the way.
And they were walking. We don't have to walk. But imagine if they had to bring all of their supplies from the start. It'd be impossible. What did they do? They lived off the land. So we need to figure out how to live off the land. And this company has actually begun thinking about that. There is water trapped in these asteroids that could be mined and could be used. Well, how are you going to use water in space? Now, one thing you could do, if you had the resources and built a big enough plant, would be to separate water into hydrogen and oxygen, and then you've got rocket fuel. But in the meantime, you can even just use the water, because you have tanks of water, the sunlight comes down and with photocells heats up that tank of water, which then sprays out a nozzle, and so you've got thrust.
Oh, cool.
And so they're thinking about that for the future, near future actually, in terms of using it on certain spacecraft. It hasn't been developed yet, but this is in the thinking process at this point. Okay, so what do we know about asteroids? What have we learned? We've had previous examinations of asteroids, somewhat. One was investigation of meteorites that hit Earth. The problem is they oftentimes partially burn up or completely burn up, or they get contaminated when they hit. Sometimes you get a pristine one if you're lucky, and they can be evaluated, especially ones in the Antarctic rather. NEAR, I forget what it stands for, was a mission that actually landed on Eros, which is a large asteroid in the main belt, in 2001. And Dawn, which launched in 2007, arrived at Vesta, which is also another large asteroid in the asteroid belt, main asteroid belt, and then orbited Ceres, another one, in 2015. And so from this, we were able to get some information about what these asteroids look like, what are their composition, but in a crude way. We do know from this information there are 3 different types of asteroids, actually. Everybody thinks asteroid is just a rock that hits. No. The D type of asteroid is a rocky asteroid, and this is most common. And they usually can reach Earth's surface because they're hard rock. Okay. So they partially burn up, but they can hit the surface. C-type asteroids are mainly carbonaceous, that is, organic material. Doesn't mean life, just means carbon-based material. And there's lots of it there may be some rock as well, but there's lots of this carbon-based material. They usually are very fragile and burn up in the atmosphere for the most part. Very unusual to hit the Earth's surface. And then there are actually metal asteroids that are just basically pure metal, and I'll explain how that came about in a little bit. So how did asteroids form? Well, in the early part of the solar system, the sun had formed, and then there was this big disk remaining. The sun formed out of the disk of gas and dust, but the rest of the gas and dust disk was still present. And pieces formed in that gas and dust. Some of those pieces went on to eventually coalesce and form planets. But if you've got a big planet, it prevents the asteroids from forming another big planet. And so you've got lots of little pieces left over, which are the asteroids. The one thing that happens that we didn't know about, and now we're hypothesizing, is that metal asteroids form when larger bodies, larger asteroids have collision, or protoplanets, meaning almost planets, have collisions, scrape off all the crust and mantle, and you're left with an iron core. That's the hypothesis. So that's how a metal asteroid would form, this kind of event. Okay. Keep that in mind, because one of the missions is looking at a metal asteroid and trying to figure out, is that really what happened? So there are 3 main missions that NASA has had, is having, to asteroids. One mission has been completed, and the data and substance that we got from it is being analyzed. And then there are 2 that are on the way. So the first one was OSIRIS-REx. That was a visit to a type C carbonaceous asteroid. So we could evaluate it, because remember, you can't evaluate them too easily when they come to Earth. It launched in 2016, and it got a sample, and I'll show you how, that actually was returned to Earth not quite 2 years ago. Another one, Lucy, is a visit. It's named Lucy, I'll show you why in a minute. It's a visit to several Jupiter Trojan asteroids, and the Trojan asteroids, I'll show you, are in Jupiter's orbit. This launched in 2021, and then finally Psyche, which is going to be visiting a metal asteroid, launched in 2023. So OSIRIS-REx, its primary purpose, there were others, but its primary purpose was to take some material, bring it back to Earth so we can investigate it. Okay. Oops. And the carbonaceous material, first of all, like I said, because carbonaceous asteroids are unusual, it's hard to get a handle on them. They're less likely to survive, and so they're special. The target was something called Bennu, which was about half kilometer in size, so about a quarter of a mile in size, so not a biggie. And spheroidal. And you see, Bennu does occasionally come close to Earth, mostly though it's in the area between Earth and Mars. One of the things it did is use the spectrometer on board to see what was there, although they wanted the sample itself because you can't get detail. What they did find was there were hydrated phyllosilicates, carbonates and magnetite, all of which means this had plenty of water at one point. What they also found was organics, maybe from another asteroid or from itself. We don't know. But there were organic material on its surface. So prime to be able to take a look at it. This was, I won't show you the satellite, but this was the arm that came down. So it hovered around this, orbited basically around this asteroid. This arm came down and touched the surface, or what they thought was going to touch the surface because they thought it was going to be hard, blow out some nitrogen gas, and material would come up and get some of it into this basket. And this was the expectation. Poof, see, right? Get the material, and then go back up and put it into a canister that's re-entry proof and come back to Earth. The way it actually did was that. It's soft enough that it went into the asteroid itself. And instead of picking up 60 grams of material, which was their lower limit, they thought they would at least hopefully reach, it brought back 250 grams of material. And you see that basically, after it's got the material, it went into that canister, which is re-entry proof. It came back in 2023, soft landed in Utah, was transported to NASA Johnson Space Center, where it was opened for evaluation at Johnson, and it was opened under pristine, sterile conditions, under nitrogen-filled boxes. But then some of the material has been distributed to other places around the world for investigation, because we want to look at it with things that can't fit onto a satellite. Electron microscopy, etc. And one of the major things that we wanted to find out, does a sample contain organic compounds that could have somehow influenced the origin of life? Like, and we'll get to that in a minute. Lucy, launched in 2021. This one is in honor of a human ancestor fossil found in Ethiopia, which the fossil is named Lucy, and therefore they named the mission Lucy, because these are the fossils of the solar system. The Trojan asteroids are here and here, it so happens, these are the Lagrange points for Jupiter. That's why the asteroids are there. And they just hang out. But the mission will go to both areas. And it's designed to get a handle on the early formation of the solar system. It's like what part the early asteroids played, how much of the outer planets are from asteroids, etc. And so what rocky and icy materials make up the giant planets? Where and how did they form? Did they move around the solar system? They have theories that maybe the giant planets moved in the solar system, that they were closer into the sun and then moved out farther. Those kinds of things. And again, how did the materials needed for life make it to Earth? So if you look at the Trojan asteroids, you have all these asteroids hanging around, and the large planets bump them. And some of them are ejected out of the solar system. Or up to the Oort cloud, for example. Some of them are ejected and become the captured Trojans. Some are ejected and become the main belt asteroids. And the plan is, and it's on its way, is to look at 6 of these Trojan asteroids around Jupiter. This is just what they look like, various sizes, various colors. So the ones that are very red may be the more rocky ones, the lighter ones may be carbonaceous, we're not sure. The spacecraft itself is 50 meters, 50 feet across, so it's a big thing. In the meantime, on the way there, they realized that they would come within basically 69,000 meters, or kilometers rather, of Dinkinesh, which is a small asteroid in the main belt. And so they rearranged it so that Lucy could get actually within a couple 100 miles of Dinkinesh and take a look at it. And the idea was just to get a look at another one, but also to check out all the instruments and make sure they were okay. And so this is the picture of Dinkinesh. It turns out it actually is 2 asteroids in one. It has an asteroid and then another asteroid orbiting it. And then Psyche is the one that's going to an all-metal asteroid. And the asteroid itself is named Psyche as well. So the asteroid is named Psyche, the mission is named Psyche. And the hypothesis is Psyche the exposed core of a larger asteroid that had a collision? And it could be something like this. Sometimes they build up and you get yourself a planet. Sometimes it's like this and you have a collision, it scrapes all this material off and the core is left. So basically it was launched in October of 23. Its arrival will be in 2029 because this is in basically the main belt. And so it has a cruise of 3.6 years with a Mars gravity assist. And then once it gets there, it will orbit several different orbits around Psyche, doing a number of different experiments, including mass spectroscopy, gravitometry, etc. Right now, it's out beyond the Mars orbit. It's about 190 million miles from Earth. Current speed is about 84,000 miles per hour, so it's fast. The maximum speed will end up being 124,000. And it uses ion thrusters. This is an experiment that also has part of the mission that NASA is experimenting with. So ion thrusters use xenon. It's sort of like taking your hand 6 inches above your palm and dropping a quarter. That's the amount of thrust. But it's constant. It's a constant thrust, and therefore constant acceleration. So it keeps on getting faster and faster and faster and faster. And that's the way of getting across the solar system for the future. This is the spacecraft, and it uses, like I said, ion thrusters. I'm about to blow your mind. Okay? There have been some updates. The Japanese developed this spacecraft called Hayabusa 2, and it went to Ryugu from June of 2018 to November of 2019. And it too got a sample of that asteroid, carbonaceous asteroid. Got a small sample, only 5 grams, as opposed to the 250 we got back. But it was a small sample. And upon looking at their sample, they found uracil. Does anybody know what uracil is? Okay. It's one of the nucleotide bases, and it's the one that's in RNA, ribonucleic acid. Ribonucleic acid in the cell takes the genetic material DNA, makes a copy of it, and then forms proteins from it. We are all proteins. That's why you have blue eyes, or tall, or short, or whatever you are. It's mainly proteins. And that's how we express our DNA. And it's RNA that does that. The thinking is that maybe in the early life on Earth, it was all RNA based. Okay, very ancient, primitive microbes that were RNA based, that then got swallowed by a bigger cell and used that RNA for its protein manufacturing, because it developed DNA. Okay? So now you're thinking, whoa, that could be something. Not anything yet.
But Neil,
Yeah.
the question, you also found the analysis already there, or it's bringing back the analysis on Earth?
It analyzed the material on Earth. It brought back a 5-gram sample that was analyzed on Earth. There would be no way of analyzing it in space, because it did mass spectroscopy and electron microscopy. Now, some people challenged, did they use the right, was it absolutely sterile, maybe it was contaminated, yada yada. Okay. Remember I said that Bennu got material back. Initially, looking at it, we knew it was carbonaceous, and we knew it was water in the past. But there's been some further examination of that material recently. Hold on to your hats. These are the 20 amino acids that are required for you to live. Okay? We have 20 amino acids that make up our proteins. Of those 20 amino acids, 14 of them were found in Bennu. Gets better. Anybody know what these are?
Basic elements. Basic elements of what?
These are the 4 bases, the nucleotide bases, that make up DNA. All 4 of them were found on Bennu recently, on the material we got back from Bennu. So, I'm not saying there's life on Bennu, but just maybe, did Bennu show us that asteroids were essential in making life on Earth? So in summary, we know there's millions of asteroids in the solar system. The main belt asteroids between Mars and Jupiter. The Trojan asteroids in the same orbit as Jupiter, and then near-Earth objects within 100 million miles of Earth. Millions of them. They may someday be used for rocket fuel. Can they pose a danger? Maybe, but NASA has plans to try and avoid that danger. And the danger is not imminent. It's not within the next 1,000 years, probably. And they can give us some information about the solar system. For example, not only the formation of the solar system, but maybe were the asteroids, the origin of life on Earth. Like that. Any questions?
Yes, how were the asteroids able to have water? Where did they need oxygen, right? So
Right. So the gas and dust cloud that formed our origins was one that was 4.6 billion years old. Remember, the entire universe is about 14.6 billion years old. So our gas and dust cloud probably came from a supernova, which means it forms oxygen besides the hydrogen, and you do have water. We're now, James W. Webb Space Telescope, now looking at protostar disks, show that there is water in a lot of these disks.
What was the size of the asteroid that hit Central America 63 million years ago?
Right.
And the second question is, if it hadn't hit Central America, where would be the state of the Earth?
Okay, so the first question is easier to answer than the second question. The first question is, it was basically an extinction level event, so probably several kilometers in size. Okay, at least several kilometers in size. If it hadn't hit the Earth, humans might not be here right now.
Because the dinosaur would continue on until whatever.
Well, maybe not. Remember, the dinosaurs were also dying out anyway because of changes in the Earth's ecosystems.
Right.
So, would they have persisted? Probably not. Would humans have become humans? Maybe still, but it's hard to say.
Yeah. But the size, when you had that other chart up, you had the big one, the middle
It was
one,
the
the
big
small
one.
one. It would have been the big one?
Yes.
Yeah.
now, would that have changed the orbit of the Earth or anything
Not-
having to do with where the Earth is?
Not enough, no. Yes, it's a big hit, but it's not enough to really change the orbit of the Earth because of the kinetic energy of the Earth has.
Right.
How much does a 1.5 meteor weigh?
That is a good question. It depends on the type of asteroid, what it's made of. For example, if it's a carbonaceous material, it's going to be lighter. If it's a metal asteroid, it's going to be heavier.
Yeah, but what's lighter, are we talking
Right.
billions and trillions of pounds or tons or?
Yeah, probably billions of tons, yes.
So to shift one of these things,
No, you're not ship it?
shift it, change
Shift
its
it.
orbit or whatever.
No, because it depends on the size of the asteroid. Yes,
Right.
an extinction level event, you're going to have multiple hits against it and, all coordinated. If it's like one that's going to hit New York and wipe out New York, that's a lot easier to shift.
Should we?
Because it should. New York,
From the
New
East Coast.
New York,
East Coast, you shouldn't be asking him that.
wait. New York, it's okay. Philadelphia, absolutely was shifting.
You mean because of the Super Bowl, or?
No, because I'm a well,
Well, yeah.
I'm an adopted Philadelphian.
So, it sounds like what we're saying here is it's possible that life on this
Oh,
planet,
by the way, go Birds, go ahead.
Yeah.
that life on this planet, the seeds of this life may have been from asteroids hitting this planet.
Exactly. We may be all offspring of asteroid,
So-
the material on asteroids.
I thought the Earth was only 6,000 years old. What happened?
So,
Been reading the wrong books again.
Yeah, I guess that book is too thick.
I don't
anyway.
think I want to answer that.
so
Good idea.
the likelihood of that happening elsewhere other than our planet is
Gigantic.
probably pretty high.
There you go.
And maybe, and therefore outside of the solar system, maybe in other solar systems, which leads to another question. Have we developed the technology yet? We're starting to be able to see planets in other solar systems. What about asteroids? Or anything capable of doing what we think we don't have that technology yet, okay?
No, but we are beginning to be capable of finding signature gases on other planets that indicate that they have life.
Okay.
For example, there is one planet that James Webb Space Telescope saw, and now another telescope saw, that has a very large abundance of something called dimethyl sulfide. Dimethyl sulfide on Earth is seen only only in organisms that produce it. So marine bacteria, plankton, that kind of particular algae, marine algae. The thinking is that this one planet called K2-18b, which was seen by Webb, is in the habitable zone and is a water world. It might very well harbor life. And there are lots of astrophysicists who now talk about this is not a star-filled universe, but a biology-filled universe.
How much of the Earth's sky has been looked at by the Webb and the Hubble?
Tiny bit. The Webb can only the Webb is great because it looks far, but the Webb can only look at a very narrow slice, which is why the Nancy Roman Space Telescope was being developed and now may be canceled.
The Romulans have a wide-angle space telescope. I saw it on eBay just last week.
How much was it? What did it go for?
But Nancy
It was in Klingon currency too.
Nancy Grace Roman Space Telescope was supposed to do that. It was supposed to look at wide swaths
You say the
and
name
then
again?
target the James Webb, and NASA's having its science budget cut in half.
Why would that be?
You don't want me getting into this.
So say the name, use the Nancy Roman, what did you say?
Nancy Grace Roman Space Telescope.
Nancy Grace Romans. That's a weird name.
That's her name. That was her name.
Oh.
I got a question. Wouldn't it make sense if it's an extinction event headed our way to blow it to pieces and let it no longer be an extinction event? That is, okay, we got New York and Philadelphia and London, but we're not losing the population of the planet. Wouldn't it make sense to turn it into a shotgun device?
It might, but we don't have the technology yet to be able to do that. I mean, you would need probably lots more thermonuclear weapons that we have to be able to do that.
Okay,
And Bruce Willis isn't doing well either, so
right.
he couldn't do it.
Yeah.
You say that these things have water in it.
Yes.
Is this like if you cracked it open, you could just drink it?
No. It's bound into the chemicals, the minerals on the asteroid. But because of the particular type of minerals that are present, we know that there was water when it formed.
So
there's not necessarily water now.
There probably is not.
everything that has mass has gravity.
Yes.
So in the asteroid, belt, as it were. Things are kind of moving around all over the place. They're not all just going one big circular pattern, are they?
They generally orbit Jupiter.
I mean, it looks like
Well,
there's-
the Trojan asteroids do orbit Jupiter, just, they follow along with Jupiter. The ones in the main belt orbit the sun. They don't orbit Jupiter. They're just
But I mean,
they're
they're-
between Mars and
But
Jupiter.
are they moving collectively? Sort of moving all over the place? That looks like it has an impact point on it right there.
Yes, but they all have, early on especially, they all had impacts. That's
So,
how
are they-
that's how the solar system
Are
formed.
they stationed relative to themselves as they move around, or are they still moving? How can I say that? Okay, you got thousands of them. Are they staying in station as they?
Now it's more civilized, but back in the early days of the solar system, there was chaos.
So when we see an asteroid, we can track which way it's coming from. Can they tell where it came from then?
Basically, yes. Maybe not back to
Return address sort of thing?
I mean, they all came from the solar system. They all formed in the solar system. They just are formed in different places in the solar system.
But comets are different.
Comets are also formed in the solar system. They're just basically further out.
They're way out.
There are two levels. There's one that are the Kuiper belt, which are the ones that are just beyond Neptune, and then the Oort cloud is a light year or two away, but still orbiting the sun, still part of the solar system.
I hope there's not a test on this later.
Okay, we got 3 more questions.
So we're worried about these things hitting Earth. What happens if one of these things has an extinction size that hits the moon? Or does any of them affect the sun at all?
It wouldn't affect the sun. If it hit the moon, it would, an extinction level event would break a lot of the moon off. Is that going to hit Earth? I don't know.
Well, it's going to hit Philadelphia or New York, that's what we want.
That's right. And it just depends on how it's hitting it.
I mean, could it hit enough chunk hit the moon to make that wobble its orbit and screw up the tides and whatnot here?
I guess that's possible, yes. But you remember the moon is you're talking about astronomical distances. The moon is basically in the Earth's backyard.
Right.
So we're talking about, if an extension level event, you're talking about thousands of years from now, because it's millions or hundreds of millions of miles away.
Anybody else? Did you have one? Yeah.
Has anybody fantasized about what an asteroid impact would be like on Earth?
Oh, sure. There's lots of sci-fi about that. There's I forget the names of them. Deep Impact is one. I think that was a comet. The other being I forget. But there've been several sci-fi books, movies, etc.
Right, sci-fi, but what about scientists? Have they come up with any ideas about?
Yeah, it's all not good.
No, it's all not good.
No.
Depending on the size.
Depending on the size, it's all not good.
Didn't we have one come into Russia?
Yes. You mean recently?
Well, like 10, 15, I don't remember what it was.
About 10 years ago.
Yeah, about 10 years ago there was one that was very small, and it shattered windows, that was all. The one in Tunguska, which was 1908, leveled the part of the Siberian forest. And that was probably because of, there's no crater though, so it was probably because of an explosion in the atmosphere.
Did people hear it? Was it heard 100 miles away or anything like that, or do you know? I've read about it, but
I think if anybody was close enough to hear it, they were
Dead.
absorbed in the
Yeah, I don't think anybody, it was just happened to be found. You know, that.
Flying over, they saw it and it's like, whoa, what happened? Yeah.
So the atmosphere, there was stuff in the atmosphere for a couple of years after that, I think.
It may have been, I'm not sure.
Okay, last question, anybody? Okay.
Well done.
Thanks.